Então, boa tarde a todas e todos. Hoje a gente tem o estudante de mestrado, Erick Cignachi. Esqueci de perguntar como fala teu nome, depois tu repete, é
Cignachi.
Cignachi. O Erick, ele é formado em técnico de TI, antes de iniciar o bacharelado em física aqui na URGS, com ênfase em astrofísica. Ele se formou o ano passado e agora ele iniciou o mestrado. O Eric vai falar do modelamento de um par de galáxias, desculpa, de um par de grupo de galáxias. Eric, quando tu estiver pronto, pode começar.
Okay, I will do my presentation in English. Thank you, Anna. Good afternoon, everybody. My name is Erick Cignachi, and I'm here to present our work that is titled Modeling the Mass Distribution of a Pair of Galaxy Groups, work that was supervised by Cristina Fulaneto and Marina Trevisan. So to give a little introduction, the current model for structure formation is given by the cosmic model lambda CDM. That stands for cold dark matter, where it predicts this hierarchical pattern of structural formation. That is, the individual galaxies that combine through gravitational interaction to form large clusters, and eventually the superclusters, composing the image that we see here as the cosmic web. This big image that I have here in the screen is the Millennium simulation that shows us the expected distribution of dark matter in a cubic region of around 2 billion light years on a side. Because the dark matter cannot be observed, the way that we have to explore the cosmic web structure is to put the simulations to the test by studying the mass profiles that interact directly with the dark matter via gravitational force. That is, if we can observe it, we can't observe it, the dark matter in this formation, we have to study the mass that traces the dark matter. So how do we trace these mass profiles to study the cosmic web? Tracing the mass profiles of galaxies and larger structures is essential an essential component to understand the physical characteristics of these objects. These objects act as great laboratories to understand better the fundamental characteristics of the universe. The very initial finding of dark matter, for example, was made by investigating the rotation curves in the galaxy scale, where it was seen that the galaxy should be much more massive than it was measured by baryonic particles only. We want to explore as wide of a variety of objects as we can, because on different scales, we can find different characteristics and behaviors of the baryonic and dark matter particles. One example would be the difference between the inner regions of the dark matter halos in the dwarf galaxies and galaxy scales, that in the inner regions they have more of a constant profile with smaller radii, and the cluster scale, that when we get to smaller radii, we have a divergence, or what it calls as a cusp. And in the constant regions of the galaxy and dwarf galaxy scales, we have what we call as a core. This is known as the cuspy and core problem, one of the open problems nowadays in dark matter research. And we also want to combine as many techniques as we can to break the degeneracies associated with each method. It's possible to use more than one method if it's possible to use more than one method to trace the mass of the same object, we want to use more than one method. We want to use all the methods that are available in order to get the best possible result. The first method that we discuss for tracing the mass profile is gravitational lensing. Gravitational lensing is an effect predicted by Albert Einstein's theory of general relativity. This effect describes that the light from a distant object that we call the source must be deflected due to the curvature of time of space-time that is caused by the gravitational field of some massive object in the same line of sight as the observer, or approximately at the same line of sight. When this effect is strong enough, we have the so-called strong gravitational lens effect, where it creates multiple and distorted images that we call the gravitational arcs. Here on the left, we have an example of this phenomenon. We have the system that is known as the cosmic horseshoe. This is a galaxy-galaxy lens system, where the lens object and the source object are both galaxies. We see that they are very closely aligned because the source almost form a ring around the lens galaxy. To trace the mass in this system, for example, we should start by assuming a mass distribution for the lens. The lens object should have a mass distribution. After assuming that, we use optimization algorithms to fit the best possible parameters for this model, in order to reconstruct the arcs as best as possible. We have to construct the arcs as closely as we can, so that in the end of the process, we get the best possible result for the mass profile of the system. Another way for us to probe the mass distribution on a galactic scale is by using stellar or gas kinematics. By investigating stellar and or gas kinematics, of course, we can use both. We can extract the rotation curves, especially in the case of spiral galaxies, for example. Here, like here we see in the rightmost image. Or we can also extract velocity dispersion profiles for galaxies with a high velocity dispersion, such as elliptical galaxies, for example, also here in this rightmost image. Then, by having when we extract these measures, we can perform dynamical modeling. And with this model, we trace the gravitational potential. And by tracing this gravitational potential, we can also trace the mass profile of the galaxy. So that's another way we can do to measure the mass profile in the galactic scale. Now, going for other scales, for example, the cluster scale. But before we talk about the cluster scale, it's important for us to define what we consider a cluster. Generally, the definition can vary from author to author, but one safe definition is to consider that clusters gravitationally bound clusters are gravitationally bound structures with around hundreds of members, like 100 or more. It's a good definition for we set up for clusters. There is some authors that consider less. There is some authors that consider more. For the cluster scale, in the leftmost image, we see a powerful cluster lens, and the method of tracing the mass for these clusters is roughly the same. Only this time we have to assume a mass model for the cluster, and not only for a single galaxy. And we also want to try to reproduce the arcs in this system. As cluster systems are much larger, it's possible to probe the mass at various different radii, because that with a large enough mass profile, we can get a lot of distorted images, like we can see in the image. Here in this leftmost image, we see a lot of arcs that are being lensed by the same cluster. There is another method too for using for measuring tracing mass profiles in the cluster scale. It is by using X-ray emission. We first analyze the distribution of the Bremsstrahlung emissions from the gas in the intracluster medium, using the assumption of spherical symmetry. That is very important to estimate some parameters that are to be used in the hydrostatic equilibrium equation, that can be used along with other techniques. That is depending on the approach. There are authors that use some other modeling together with the hydrostatic equilibrium equation, and they use that to finally trace the system mass. We also have some other methods, such as analyzing member kinematics, members of the clusters, via number density, where we have to assume that the number of galaxies trace the dark matter, that is, where in the cluster we have more galaxies, we have more dark matter. Where we have less galaxies, we have less dark matter, and we use that to trace the profile. And and also by using the Sunyaev-Zeldovich effect, but I will not get much into detail of these three methods. All these techniques also allows us to investigate the substructures in more complex systems. For example, as the ones that are gravitationally interacting, for example, which gravitational interaction is a particularly important event in a hierarchical universe. The study of gravitational interaction plays a crucial role in understanding the large-scale structure. It is through either mergers or assimilation of smaller objects, such as individual galaxies, it's by this method that the individual galaxies can evolve and combine, eventually into larger structures such as clusters. Interactions can be studied using different techniques in different scales, the same way as tracing mass profiles in the different techniques in different scales. In galaxy regime, we can detect interactions by finding disturbances and asymmetries for the luminance component of the galaxies. For the cluster regime, we have to look for the same disturbances and asymmetries, but this time we want to look at the X-ray emissions for the intercluster medium of both objects. One clear example of this is the bullet cluster that we have here in this right image. We can see here that even if the dark matter that is traced by these blue halos is no collision, and there is no evidence that they pass through one another, we can see that one cluster indeed pass through one another because we have these pink halos that describe the intercluster hot gas that is collisional. In that way, we can use the X-ray emissions in order to see and to find these gravitational interactions and possibly mergers. These interactions happen constantly in our universe and can give us an idea of what the large-scale structure looks like in our universe. So far we've been focusing on the more studied structures of the literature, galaxies and clusters, but to go from the regime of an individual galaxy to galaxy clusters that have hundreds of galaxies seems too much of a leap. And we know there are many structures with less than 100 of galaxies that are still gravitationally bound. And these structures is what we call galaxy groups. So, galaxy group is an agglomerate of 2 or more galaxies gravitationally bound, while we still have less members than the definition of a cluster. Here we have an image of 2 groups of galaxies. On the left, we have a famous one. That is the Stephan Quintet, a group of constituting of 4 galaxies. And on the right, we have the Leo 1 group with 12 confirmed members and 30 unconfirmed members, showing that groups can very well reach the tens of galaxies, like 10, 20, or 50 galaxies, but of course, that also varies from outer to outer, what he defined as the limit between a group and a cluster. So why precisely are galaxy groups important? According to the 2DF survey, around 55% of the galaxies in the local universe are members of galaxy groups that are constituted of 2 or more galaxies. And furthermore, according to Fukujita, galaxy groups host most of the mass in the universe. Only the discoveries show us that if you want to have a better understanding of a universe, we certainly need to look truly truly understand galaxy groups by studying its properties, such as mass profiles and kinematics. And after all this context, we can introduce the system that we are studying. So the Helms-18 system consists primarily of a submillimeter galaxy that was detected at redshift 2.4 that is being lensed by a massive object in the same line of sight. This system was but the system was observed via interferometry with the ALMA observatory in the band 7, which revealed 2 arcs with a peculiar configuration. Here we can see an image of these arcs. Notice how the arcs are not centered in the same point. This fact sparked some curiosity on us, and we went to check the optical counterpart of this emission. Of course, because this is a galaxy with an emission on the submillimeter, we cannot see in the optical wavelength spectra. So we want to see what can we, if we look on the optical wavelength, what we will find. We found the optical counterpart to the system in the Slow Digital Sky survey. And we found that in that position, we have two peculiar objects. Here, a zoom of them. That is a zoomed image of this blue region overlapped with the ALMA detector arcs. We see that each of the arcs is already centered in each one of the arcs are centered in one of the central objects. The most blue object was cataloged as a star in the SDSS, but by an analysis of the colors and the context that it was inserted, of course, because supposedly being a less object, we suspected that it could be a quasar. That we will refer as a QSO candidate. The most red object is cataloged as an early type galaxy that we will refer as the central ATG with, and it has a spectroscopic redshift already measured by the SDSS. It is around 0.6. One of the things that we can do quickly with lens systems is to have an initial estimate of the lens object, the mass of the lens object, the mass of the structure that is lensing the source galaxy that gives us the light for the arcs. By doing a measure of the separation of the arcs, we saw that the separation was typical of a group scale lens. That is, that raises us the question: is the lens object of the system Helmholtz in a galaxy group? So to answer this question, we set out some objectives. We want to confirm if that central object was indeed a QSO, a quasar. We want to determine which galaxies are part of the structure that act as a lens. We want to determine the properties of the lens object that are mass and velocity dispersion, for example. We want to determine the properties of the central galaxies. And we want also to determine the probability of interaction if there is more than one group that is lensing the submillimeter galaxy. That is, if we have two galaxy groups, for example, in the lensing the same galaxy, we want to know if they are interacting in any way. To achieve these goals, we need spectroscopic data. And then we therefore carried multi-object spectroscopic observations using the Gemini telescope. Here on the left, we have an image of the telescope that was used on the observations, the GMOS. That is localized in the Gemini South Observatory in Chile. That is the image on the right here. And well, how do we select the target that we want to observe? By using the SDSS photometric catalog, we selected the target galaxy in the field of the Helmholtz 18, prioritizing first the galaxies in the right sequence, defined by these colors from 0.9 to 1.5 R minus I. Galaxies in which the photometric redshifts are around the redshift of the center of ATG, that is around 0.6. And other galaxies, bright galaxies in the field, and regardless of their color. And with this criteria, we found 76 galaxies that were eligible for our multi-spectroscopic observation campaign. Here we have some details of the mask that we used. Some of the more important data that we have here is that the range that we used was from 3500 to 1600 angstroms. This range is enough to capture some of the absorption and emission features that help us to determine what redshift the galaxy actually is. The total exposure time for each mass was around 4 hours, and both of the central galaxies were observed in both of the masks in order to get a better signal to noise ratio for these specific objects. So once the raw observations have been obtained, we have to reduce the data so we can be properly analyzed. The data was reduced using the standard GMOS data reduction pipeline. We took into account by subtraction, flat field correction, quantum efficiency correction, wavelength in flux calibrations. And these are some of the spectra these are the spectra that we obtained for the central galaxies. And in the left, we have the ETG spectra overlapped with the SDSS spectra that we already have, because, as I said, they already have a spectra to define the spectroscopy redshift they already have, but is overlapped here for means of comparison. In the right, we have the QSO candidate spectra, and by inspection, we can clearly see that this is not a star spectra, but is indeed from my galaxy. And one example I can give you is from the width of the H beta line. It's probably a galaxy with very high, with gas in very high velocity. So we will call it a quasar. And then we refer to this central object as a quasar or QSO from now on, totally discarding the possibility that this object is in fact a star. In total, discounting objects that were incorrectly cataloged as galaxies in the SDSS and were actually stars, or objects that were too faint for even an extract spectrum, we obtain around 70 spectra. Okay, we have this 70 spectra, and we want to estimate redshift to see who from them can possibly be members of the lens object. For that, we use the XCSAO and MCSAO task from the RVSAO package in IRF to determine the redshift of the observed galaxies. The MSAO task is mainly used when the analyzed galaxy had emission lines, while the XCSAO task was used in all other cases. While the EMSAO task works by marking the emission lines from the spectra and calculating their dislocation from the rest frame, like we see here in this image, the XCSAO task works by cross-correlating a section of the spectra with many other spectra in different redshifts that we call the model spectra. And by doing this cross-correlation, we can find the ones that best correlates with the data. Consequently, we can find the redshift of the or the best possible redshift for this spectra and this galaxy. Okay, we estimated the redshift of these 70 objects, and we select the members, the possible members of the structure, according to this criterion. That is, the redshift must be between 0.596 and 0.608. It's a range that encompasses 3,600 kilometers per second. And considering that the typical velocity dispersion of galaxy groups is around 150 to 300 kilometers per second, it's reasonable to assume that other galaxies can be ruled out as candidates for membership. In this image, we can see that the distribution of galaxies in the redshift, we can see the distribution of the galaxies in the redshift space. On first look, we can see the distribution looks like a bimodal distribution. And when we localize the two central galaxies in the graph, we see that each one is approximately at the center of their respective mode. It's also important to highlight that we found 21 members inside this range. I believe I didn't say that. Okay, continuing. To precisely quantify the bimodality of the distribution, we use the Hausmann-Volmer bimodality indicator that can tell us if the distribution is in fact bimodal or just a unimodal distribution with some crazy variation. But to use this indicator, we have to use this double Gaussian fit that we did, and by using the parameters of this double Gaussian fit, if this value of D is bigger than 1, we have indeed a bimodal distribution. And by using our values defined by the fit, we got around a value of D of around 2.1. So that tells us that in fact distribution is indeed bimodal, and we in fact have two galaxy groups in the same line of sight, lensing the same galaxy. Therefore, going forward, we will treat the lens object of the system as two galaxy groups, one in front of the another, that are lensing the same galaxy. That was in Redshift 2.4. Now that we know that we are dealing with two groups of galaxies, we wish to know which galaxies belong to the group on the front. That will show you the front and the back. When I say the front and the back, I mean in the redshift space. Though when I say the front, well, I mean the group of the galaxy group with the lowest redshift. When I say the back, the galaxy group with the highest redshift. To decide what galaxy belong to which group, we used two clustering algorithms. The first one being the M-cluster clustering algorithm, and the second one being formalism that was described in this paper by Willman in 2005, and was implemented in a similar way we implemented the algorithm, the formalism, in a similar way to Munoz in his paper in 2013. After the clustering, we used the gap and byweight estimator, the GBE method, to calculate the velocity dispersion for each of the groups. Here we have an image of the sky plane where I marked all the 21 possible galaxy members with the two central galaxies. So first, talking about the clustering method of M-clust. M-clust is an R language package and is used for normal mixture modeling and model-based clustering. So by using the EM, that is the expectation maximization algorithm, we tested different models to find the one that aggregates best the objects in the three-dimensional space. And to find the model that aggregates best, we find the model with the highest big value, that is by the Bayesian information criteria. Of course, when we talk about big value, we usually want the lowest big value, but by the way the M-cluster defined mathematically, the way that they calculate the big value, we actually want the highest when in this code, in this software. In the image, we can see the best possible fit for the system. We found that the structures are separated in the velocity dispersion, in the velocity of this, in the velocity of recession, that is the redshift. And after the clustering process, we use the GBE method and find that these velocity dispersions for the groups are 242.9 kilometers per second for the group centered in the ETG, and 197.5 kilometers per second for the structure or the group centered around the QSO. These values are well within the expected for galaxy groups velocity dispersions. And the second method is a formalism by Willman that I talked about before. And is done by an iterative process. We start by defining the initial sigma observed that we have here in the first equation, that only depends on the redshift of the central galaxy in the group. By using this value, we define a cylindrical shell of redshift angular space. The shell in the dimensions of redshift is this delta z, and in the dimension of angular space is this delta theta. Delta theta is given by the expression that depends of c, where c is the speed of light, h of c, that is the Hubble constant in z, d theta, that is the angular diameter distance in the redshift z, and b, that is the axis ratio of the cylindrical linking volume. This value of b is defined by dark matter simulations, and we found that these simulations put this value of b of around 3.5. That is the value that we ended up using in our process. Having defined this initial shell, we see which galaxies are inside it to be gravitationally bound, and calculate the velocity dispersion via the GBE method that I showed you before. We use the new value of the velocity dispersion that we calculated as the new sigma ops that was probably defined by the first equation. And we repeat this process of defining the new redshift shell and the new angular space shell until the number of galaxies does not change between subsequent iterations. Here I have the first and last iteration for both of the groups. I show only the redshift, the shell in the redshift space, because in the angular space there wasn't much changing. In the image, we can see that initial and the final state for the QSO is almost identical. There is no galaxies that are excluded. But for the group centered in the ETG, we get that one red galaxy that does not belong, according to this method, to the ETG-centered group. But this galaxy did belong to this ETG-centered group in the M-class method. So given that this red galaxy is close enough to the limit of uncertainty right in the first iteration of the program, to almost be accepted, we decide that we will do the rest of analysis using the both methods, either considering this red galaxy as part of the ETG group and not considering it. So the velocity dispersion for the group centered in the QSO is the same as the M-class, because the grouping got the same galaxies. But removing the red galaxy, we get a smaller value for the velocity dispersion of around 143.7 kilometers per second. That is also values within the expected range for galaxy groups. Okay, given this two formalism, we have here a little summary of what we found. The important takeaway is that the formalism of Willman and the M-class method both have the same number of members for the group center in the QSO. But for the group center in the ETG, for the formalism, we have only 8 members. That one red galaxy is excluded. And for the M-class method, we have 9 members. By using this new separation of the members, we can calculate the virial masses. So assuming virial equilibrium for the groups, we use this calculation defined by Beers in 82 to calculate the virial mass by this equation that is defined by NC, that is the number of objects in the group or cluster, VI squared, that is VI is the relative velocity of one member in relative to the center of the group that it belongs, and Rij is the angular distance between 2 members in the same group, the YASM member and the JSM member. So both formalism of Willman and M-class method agree of what galaxies belong in the group of the center around the QSO. So they have the same virial mass, that is 9.6 times 10 to the 12 solar masses. And they, of course, disagree on the number of members for the group center in the ETG. So they get the virial mass of 3.4 times 10 to the 12 for the formalism of Willman, and for the M-class method, we got 8.6 times 10 to the 12. Furthermore, we also did another analysis. This analysis was the stellar population synthesis by using the PPXF algorithm by Capellari in 2023. In order to calculate the stellar mass in velocity dispersion and stellar velocity dispersion of both of the central galaxies, because we have galaxies with good signal-to-noise ratio, we were able to do the stellar synthesis of these objects. We found that for the early type galaxy, the ETG, we have a velocity dispersion of stellar velocity dispersion of 314 kilometers per second, and a stellar mass of 4.92 times 10 to the 11 solar masses. We can also see in the image that the fraction of the stellar population used in the synthesis was mainly of higher metallicity and of old age. Also, these values are in agreement with what we would expect to find in an early type galaxy. On the other hand, the synthesis for the QSO, now I am talking about the galaxy, the QSO, resulted in a stellar velocity dispersion of around 162 kilometers per second, and a stellar mass of 1.14 times 10 to the 11 solar masses. In this case, we see that the population here in the plot on the right used was mostly of young stars of young age and lower metallicity. So finally, we are given that we have two galaxy groups, we want to find the probability of interaction between them. So by treating the system as a two-body problem, we apply the method described by Beers, assuming that the groups start at separation 0 at the first time in the history. No, they start with separation 0 at t equals 0, that is the start of the universe, and that they are approaching or moving away for the first time in the history of the universe. For the bound case, that is what we want to study, we have these equations of motion, where r is the separation between the bodies, t is the elapsed time since the start of the universe, v is the relative velocity between the objects, m is the mass of the clusters, rm is the separation between at the maximum expansion, chi is the so-called angle of development. This system of equations can be solved by adding two other relationships that are these ones. There are parameters that these two equations are dependent on the parameters Rp and Vr. They are respectively the relative velocity along the line of sight of the central galaxies and the projected separation between the central galaxies. The Rp is the relative velocity along the line of sight. No, sorry. The Vr is the relative velocity along the line of sight. And the Rp is projected separation between these central galaxies along the line of sight. Here in the image, we can also see what is this alpha. Alpha represents the angle between the groups in the plane of sky. We see that there is a degeneracy. So we can have more than one solution. With these equations, we write down Vr of chi, and we rewrite, of course, these equations by substituting, by creating an equation of Vr of chi, the angle of development, and alpha of chi, and we parametrically plot the solutions ranging from chi from 0 to 2 pi as the black solid line in this image. We have also plotted the Newton's binding criterion, that is the equation on the bottom left. We can as well, we also plotted the measured relative velocity of the group in this image, that is in blue, that is this line in blue with the uncertainty. So we can see that for the solutions for our relative velocity are where the blue line crosses the black line. And we see that for our relative velocity between the central galaxies, there are two solutions to the system. It's also good to highlight that both are on the left side of the Newton binding criterion. That is this red curve. So they are considered bound solutions and not unbound solutions. Of course, I will highlight that this is for the M-class model, because this graph will look different in the formalism of Willman, because the mass of both of the groups are different in the other formalism. With an integral in the phase space of this graph, we can find the probability of the object being in one of these two states. The result that we got for the two possible groupings, that is using the M-class model and the formalism of Willman, is a probability of 58% of interaction for the M-class grouping method. That is, they are bound and they are approaching each other with a 58% probability. And if we use the formalism of Willman to define the galaxies, what galaxies belong to what group, we have a probability of 47% of the interaction between for the grouping probability of 47% for the interaction for they are in the bound case and they are approaching. Okay, so after all that, I will talk a bit about our ongoing work. We are currently building a gravitational lens model with the aim of reconstructing the source and giving us the best description of the lens object mass profile. That is, we want to find the shape and reconstruct the submillimeter galaxy that we only saw as arcs. And we also want to find the best possible description for the mass profile that is lensing this submillimeter galaxy. And one of the ways that we can do that, as I described right in the beginning of my presentation, is by a gravitational lensing model. To do this, we are first using the PyAutoLens software, and we are also using a variety of math models in order to find the one that best reconstructs the source. So at this stage, we have these following objectives. We want first model the gravitational lens without the kinematic parameters that we obtained until now. Then we want to model the gravitational lens with the kinematic parameters that we obtain, like the velocity dispersion of the groups, to compare with the previous model, to see what differences does it make when we get kinematic description of the system before doing the lens modeling. And we want to also estimate the dark matter and baryonic component fractions of the lens object in order to finally get the most complete description of this gravitational lens system and lens object. And we're going to do that by estimating the baryonic mass, given that we can do we've done a stellar population synthesis for most of the galaxies that are in the groups, and we can estimate the total mass via gravitational lensing. So subtracting one from another, we get the total dark matter mass from the system. So in conclusion, in this work, we got for the following results. We got 70 galaxy spectra in the Helmholtz-Zittin region. We found that we have 2 galaxy groups lensing the same object, but we found that we have a low number of members in both groups. We have 8 or 9 for the group centered in the ATG and 13 for the group centered in the QSO, which we consider to be a low number of members, because we initially placed to model the kinematics together with the lens. But given that there's no low number of tracers, because we have only 8 for the first profile and 13 for the second profile, we decided to opt for more simple modeling. In the start of the project, we thought that we could have around 20 to 30 galaxies belong to the same group. But when we found out that we had 2 groups, it becomes severely more complicated to model this system. We also obtained the virial masses of the groups, and we found the interaction model between the groups with probabilities of 47 or 58%, depending on the clustering method. And it's also important to highlight that the possibility of interaction, that is around the 50-50 mark, may affect the measurement of the virial mass, because if we are in virial equilibrium, if you are in fact interacting, we cannot be in virial equilibrium. Therefore, we may have problems with the virial mass estimation. So that's it. Thank you, and feel free to ask any questions.
Thank you, Eric. Questions from the audience? Okay, I have one. Eric, you went very fast in the part regarding the modeling of the lens. So which data are you using for that?
Okay. So,
and congratulations for your talk. It was very nice.
Okay, thank you. So to model a lens system, the main data that we have to use is the lens image. even if this is the just a preliminary image, we can already see here what is the main data that we use. You can see here that we have both of these arcs in the image, right? And these are the arcs that are shown in the beginning of the work that are detected as the submillimeter galaxy. What we do is we define we define a mass profile. We assume a mass profile that can be a power law, can be an NFW, can be more complicated profiles, and we use them to trace these pixels that we have here onto a single source in the source plane. We do that by optimizing the parameters of the mass profile, and we variate them in order to get the best possible source. And with the algorithm, of course, have a lot of metrics to determine what is the best possible source and to what direction the parameters need to go to get to this best possible source reconstruction. You can also give the mass model some constraints, some priors, so he can know where to start to look for these parameters to define the mass model, the mass profile. What we plan to do is first let the algorithm do its thing. It starts by randomly guessing the parameters and then gradually optimizing these parameters to get a better source, and we will get the result. After, we want to use these values of velocity dispersion that we can use to define a mass profile as priors, so the lens modeling know where to start to look, and then they know. And then we want to see if by knowing where to start to look, they actually get to a better result. So the way we can measure the impact of doing some kinematic analysis before doing the instead of only doing the lens modeling. So the main data that we use is the pixels of the arcs, but we can also use the kinematic information if we have so.
Okay. More questions?
I have a question.
Okay, go ahead, Miriam.
You have why there is a big difference between the determination of mass? I think that is QSO using the two methods.
So why there is the big difference between the both different the measurements of mass in the both formalism?
Yes. Let's
so
see.
No, the mass measurements are here. Yeah.
Here, yes.
This big difference, you mean?
The TG, okay, the galaxy that you have.
Yes, that is because one of the galaxies is not included in this one. Galaxy is also in a really far distance from the other galaxies that we can see. By removing this galaxy, we actually are getting a much more compact group, and that makes it so the estimation of the virial mass is substantially smaller, but is in the same order. Both are in the 10 to the 12 solar masses. So I wouldn't say that is such a big difference, but it is indeed a big difference. And it's because this galaxy is not being considered in one of the groupings, in the other grouping it is being considered.
Okay.
Okay.
Thank you.
More questions?
You're welcome.
I have one more. That is, you showed that you got the pre-imaging that you selected the galaxies inside. Was it from SDSS?
The pre-imaging? No. Yeah, I didn't show the pre-imaging. This is the this is from the SDSS. This is just so we would check the counterpart of the lens, because we found the design system, it was very peculiar, and we want to see what in the optical wavelength that is in this space, and we found these two objects and overlapping the images, we found that these arcs are around both of these galaxies. We also found that this red galaxy here had some spectroscopic redshift, so we kind of had an idea on where to look, on what redshift to look. By that, we can also select the telescope, and we use some pre-imaging from Gemini to select the galaxies that would be observed according to this criteria that I described in this slide.
Okay, my question was like, there have been some data releases, for instance, of HSC in Subaru. I was wondering if this system might be there because there's some narrowband imaging that might get redshift. So I was just wondering this.
Yes, so quite recently we actually took a look again in the system because we have a low number of members and we all obviously want to get more, but we went to look at precisely these coordinates in these new surveys, and we haven't found another image for the Helms-18 system in these newer surveys.
Okay, thank you.
Another
Go ahead,
question. How deep is your image? Do you expect to see how the exposure time is enough?
The exposure time was 4 hours, I believe.
4 hours.
I have here the
Spectral, no?
For the collective exposure, the total exposure time but for each mask was 4 hours. So for the central galaxy, we got around 8 hours of exposure, and for the rest, we got 4 hours.
Okay.
So, but we shifted the wavelength 3 times for each observation to cover the gaps of the CCD. That is these blue bars that we see here. So the exposure was also divided in 3 instances of observation.
Mm-hmm. Okay. Thank you.
Okay, thank you.
More questions? If not, let's open our microphones and thank Erick again for the very nice evening.
Okay, thank you.
Good job, Erick. Can stop the YouTube.
Sim, terminada a apresentar
Terminando.
a live.